Hi, and welcome to another lesson in the physics video series. Today we're going to continue our discussion on the PEKE conservation that we began in the last video. In the last video we discussed the energy transformation between potential to kinetic in an object sliding down a ramp. We're going to extend this concept into the object sliding along the roller coaster. And as you can see in this diagram already, there are many similarities. Alright, let's get started. The general concept of an object sliding down a ramp is immediately applicable to an object rolling down a roller coaster. In the two diagrams I have overlaid, you can see that at the top of the hill and the top of the roller coaster are literally the same position, but in just two different diagrams. Then the object slides down the ramp or rolls down the roller coaster to the bottom, and again, you see they are the same position. And then of course halfway down is marked here. So we have points A at the top, B at the bottom, and C in the middle. Everything that applied at point A on the ramp is exactly the same as point A on the roller coaster. And everything that applied at the bottom, point B on the ramp, is exactly the same on the roller coaster, including the mathematics for the final speed at the bottom, the Vmax, which was root 2gh. And of course, at point C, which was the center of the height, it is halfway down the hill. Again, this is the same position, except it is rolling down the roller coaster rather than sliding down the ramp. And so here we have a conversion between potential energy at the top to kinetic energy at the bottom. Let's take a look at the bar graphs and see the energy balance. We know that at point A, the roller coaster car is the highest point in the path. And we know that path independence of energy transformation can be demonstrated on a ramp and on a roller coaster, and you get the same results. So, at the top of the hill, on the way down, the potential energy, which is at its maximum, will then decrease, and it will be transformed into kinetic energy as the roller coaster car gains speed. And you could see at the halfway point that the potential energy has decreased somewhat, and of course the kinetic energy has increased by the same amount as the potential energies decrease. And then of course at the bottom you can see that all of the potential energy has converted into kinetic energy. Now we have an extension here where the roller coaster goes back up the hill, and of course in going back up the hill it loses kinetic energy and reconverts back to potential energy. It should be very obvious now in this full view of both diagrams overlaid against each other. You can see that as the object rolls down the hill is the same as sliding down the ramp, and the potential energy, which was maximum at the highest height, became minimum at the base. And then of course the exchange takes place where the potential energy converts into kinetic energy. As we mentioned before, this roller coaster car rolls back up halfway, but this particular box does not slide back up any ramp. Of course it could if you put one there. Let's take a look at a simulation to see how the potential energy converts to kinetic energy and back again as the roller coaster car rolls down the hill and back up again. Here we have a simulation designed to show you the roller coaster, and on this simulation I have a little orange roller coaster car that will roll down the hill and come back up again. I've turned on the velocity vector so that you could see velocity at all times. Of course, the vector will grow or shrink depending on the velocity at any moment in time. You could expect that at the top, when it first starts to roll, you would have a shorter arrow. And then, of course, as you descend, you would have a growing arrow until it gets to the bottom, when the kinetic energy, which is shown here to be 0, has become the maximum, and the PE, which is shown to be the maximum, has decreased to 0. And then it reverses its process as it ascends back up this hill. All right, let's take a look at that. Here we can see that the car is beginning to descend, and the velocity arrow is growing. And here it is maximum. And then, as it goes back up the hill, it slows down and stops, and reverses itself. And then it returns to the original position. And stop. Now, what you noticed was that this KE, which was a red bar, and this PE, which was a blue bar, they increased and decreased reciprocally. Let's take a look at these two bars as the roller coaster goes down and back up the hill. So here we start again, and we see that the speed is increasing, the vector arrow is growing, and the kinetic energy bar is increasing. until it gets to the bottom and it's at maximum, and then it begins to decrease while the PE blue bar increases to its maximum. I'm going to run the simulation again, and this time I want you to focus on the exchange of PE for KE in this bottom left corner, as well as this purple bar, which stands for mechanical energy, which is the total energy. And you'll notice something, that this purple bar will always be the sum of the P plus the K. Let's run it. You see, as the blue decreases, the red increases, and here we are at the bottom with the maximum velocity. And now we're back up to the top. We have 0 KE, maximum PE, and let's reverse the process. There we are, maximum speed again. And all the way back to the top. Let's run the simulation one more time, pausing at the middle point, the bottom, the middle point again, and the top. Here we go. So you can see the blue bar is decreasing and the red bar is increasing. And here is the exact point in the middle where the KE equals the PE. So the PE decreased, the KE increased. And if I continue, you can see how the PE decreased to 0 and the KE increased to its maximum. And if I continue, there was the halfway point again. And then finally, as it gets to the top, 0 KE and PE is maximum. Let's reverse the process and watch it again. There's your halfway point. There's halfway point going up. And finally, the car reaches the top. So in conclusion, you can see from the static diagram what we did in the simulation was start the roller coaster at the top, roll it down through the middle to the bottom, and back up through the middle, and in our simulation we went back up to the top again. And the whole time, the PE and the KE exchanged energies back and forth. The main idea for conservation of energy is that you are not creating or destroying energy, but you are converting it between different forms. And this is the reason why the PE and the KE value bar graphs exchange their values as the roller coaster descends and then ascends. I hope you enjoyed this video, and I hope that this concept of the conservation of energy has been made abundantly clear by comparing the ramp to the roller coaster, and you see the path independence. It doesn't matter if you're going straight down, diagonally down, or on a curve in a roller coaster. Either way, at the top of the hill, you have maximum potential energy, minimum kinetic energy. At the bottom of the hill, they reverse, and you have maximum kinetic energy and zero potential energy. And of course, halfway through, the energy exchange is at an equal value. Thank you for watching, and I look forward to seeing you in the next video.